Good afternoon. My name is Sima. So right after Evan has told you about the limitation using wearable devices, I'm here to tell you we can use wearable sensor data from UAS and the LEAR to detect infectious diseases. Wait, where this is the Okay, great. Before diving into our approach, let me start with the motivation behind it. So, having lived through the COVID, I don't think I have to reiterate the troubles caused by the pandemic. But the real problem for researchers is that infectious diseases spread silently, often through clusters of people who are not aware that they're sick. So this makes containment extremely difficult. Traditional methods of tracking infection, such as widespread testings, are expensive and well, like Evan just pointed out, wearable devices are also expensive, but compared to lab tests and clinical trials, wearable devices are relatively cheaper. So what we really need here is a non-intrusive, real-time detection system. So, however, personal health data is very noisy. It's highly individual. Too many factors interact in a complex way to influence health altogether. So it's very hard to isolate signals related to infections only. And also there's huge individual heterogeneity, which means everybody reacts to the illness differently. So we don't really have a one-size-fits-all kind of solution. I understand that there are many efforts put into detecting COVID, but I still believe that we are in the best position to tackle this problem, and now is the best time. I have 3 reasons. First, wearable adoption is surging. So in the future, they may be as common as smartphones. And the users are increasingly more comfortable with sharing their sharing their data with researchers anonymously. So this gives us access to this relatively cheaper, high resolution, high granularity health data at scale. Second, I want to bring up transformer model, which is the backbone of the smartest AI today. These models excel at detect correlations and patterns, making them a powerful tool for analyzing health complex signals. And third, we have the unbiased high quality data set from UAS and the LEAR. So this blend of rich data and cutting edge AI positions our study to make some real progress. Given all the reasons I listed, we believe that an effective detection system should meet these 4 criterions. First, it has to be probability sampling to reduce bias. Second, it has to rely on passive data collection because this minimizes costs and makes the system easier to scale. Third, we have to solely rely on unsupervised learning because without need for any human input, labeled data, any assumptions, the system just can be more adaptable, more scalable. And finally, I believe we should use transformer data simply because it's the best. And here is just a slide demonstrating how noisy health data can be. On the left, we see change in heart rate over time for COVID positive and negative group. And at the aggregated level, we can see very distinct patterns. And on the right, we see similar plots, but for a single individual with and without COVID. Can you tell which figure reflects the impact of COVID? Which plot carries COVID? No? Thank you. That makes my point. It's actually the one at the bottom. The x-axis 0 point, I don't know if you can see it, 0 point on X marks the self-reported diagnosis date. And these are the startle signals that we need to pick up. With all these challenges in mind, our research objective is clear. We want to develop an individualized early warning system for infectious diseases. We use COVID as an example, but the system can be generalized to other illness with measurable symptoms. Our system operates entirely unsupervised. We have the self-reported diagnosis date, but we only use that to evaluate model performance, not for training. I can skip this. It's just a brief introduction of LEAR and UAS, and this shows the representativeness of our data, of LEAR data. Now let's talk about the data we collected. We have hourly level Fitbit features. We have hourly average heart rate, total step counts per hour, the time in different activity levels, and we have gait cadence because we believe you walk differently when you feel sick compared to when you're feeling well. So how you walk can be a strong indicator of health. And as you can see, each feature follows a different pattern. Some are more stable, some carries more variance, some are continuous, some are sparse. And that's all these subtle variations are that's all we need to start detect infection. That's all of our input. Since our model is determined to do individualized model, so we make sure that the positive period and the negative period came from the same individual. So from the same individual, we collect pre-COVID as a baseline, during COVID as a COVID inference, and then for the negative data, we have data that's 3 months after the diagnosis. And we also use the first half for training and second half for testing. This slide illustrates the core idea of behind our methods. I wouldn't go into the model's architecture. I just want to briefly explain how detection happens unsupervised. So imagine we have a time sequence like what we have on the left, that there's no anomaly in it. And I use 2 circles to highlight in each circle I highlight a focal time point and its neighboring time points in each circle. Since the sequence is smooth and continuous, so within the circle, the similarity should be high, right? Because it's and between the circles, the similarity is still high because there's no anomalies in it. And now let's consider another situation. On the right, there's a bump in the data. Again, within the circle, the similarity should be high because, again, it's continuous smooth. But between circle, similarity drops because there's a clear pattern switch. So through measuring this discrepancy between local similarity within the circle versus global similarity between the circle, we can detect anomaly. And that's the simple logic behind our algorithm. Here I present the results. The 4 column sequences presents the heart rate across different time period. Well, we have positive training, positive testing, negative training, negative testing. The blue line represents the anomaly score. A higher anomaly score signifies a stronger pattern shift. I want to point out 2 key points. First, early detection. The detected anomaly onset appears days before the self-reported diagnosis date, marked as 0 on the x-axis, showing that our model has potential for early warning. Second, the model effectively distinguishes between the positive and negative period, showing that it's capable of identifying signals only related to the infection. So far, our model is still static, but we promise to make a real-time detection. We don't have permission from Fitbit to stream their data in real time, but we can simulate a streaming environment using this sliding training and testing windows. And here are the results. And again, the blue line represents the anomaly score. And again, it indicates, it correctly points out the symptom onset time. Another interesting observation is the presence of two clusters in the detection. The first clusters align with symptom onset, occurring around time 0. The second cluster appearing around hour 500 to 600, roughly 20 to 25 days after diagnosis. And we believe that might be the symptom onset. That's when people recover from COVID. So thank you. So thank you for listening. We have developed this transformer-based unsupervised model that can be utilized as an early warning system. We use COVID as example, but we don't have to. This can be generalized to any other illness with measurable symptoms. We have some exciting future directions, like we can incorporate known disease patterns so that the model can identify a specific health condition, or we can use explainable AI to fine-tune the model. So what we have done is just a start, right? And I truly believe in the potential in this system. And I'm happy to take any questions. Oh, and I also want to say thank you to everyone who contributed to the foundational work behind UAS and earlier. Thank you.